The most commonly used model of atoms and molecules in organic chemistry is the Lewis model. And the Lewis model starts with the Lewis dot diagram, which is a representation of the valence shell of an atom. And so here we have carbon over here, and you can see that it has the two electron shells. The inner shell is the core, and it's completely filled. The outer shell is not filled. We think of these shells as being filled by 8 electrons. There's only 4 in here, and so carbon has room for 4 bonds to other atoms. And so carbon, here's the Lewis dot diagram of that. We're just showing the valence shell. We're not showing the inner shell or the inner core electrons, because these are the ones that are the bonding electrons, or at least we're modeling them as the bonding electrons. So carbon, like I said, when we think about these atoms bonding, they bond to give an octet in their valence shell, and so carbon can bond to 4 or form 4 bonds. Nitrogen can form 3. This is a lone pair, and each bond is made up of 2 electrons, so there's no more room in this lone pair to form a bond. It's already that orbital is already full. We've got an oxygen that has space for 2 bonds, and fluorine has space for 1. Do notice that hydrogen over here is kind of hanging out. It actually just has the 1 electron here. It doesn't have an outer shell. Well, I mean, its outer shell is the same thing as its inner shell. It only has 1 shell of electrons. And so the maximum number of electrons that it can have in its shell is 2. So it just forms 1 bond. In organic chemistry, we're really just focusing on hydrogen, carbon, nitrogen, oxygen, and then the halogens. And that's really the main focus. We're not trying to draw Lewis dot diagrams for metals, just for the organics. So we are driven by the octet rule when we are forming bonds, and so that then allows us to make a lot of molecules, or think about how the molecules might be formed. We know that carbon needs to have 4 bonds, so here is 1 carbon, here's another carbon. Each of those carbons has 4 bonds, this one in the middle to 2 hydrogens, then to 1 carbon, and then to an oxygen. This one on the right-hand side to 3 hydrogens, and then to 1 carbon. Oxygen also has an octet. It actually has 2 lone pairs that's not being shown here, and then it has those 2 bonds. We could take this molecule apart and draw another draw another molecule with, it's also valid. And let's see here. We'll put oxygen in the middle this time, and then put 2 CH3 groups on either side. We call those methyl groups, as you will learn soon enough. And so this is a type of molecule called an ether. It's dimethyl ether. I know it's called methoxymethane up here, but most commonly called methyl ether or dimethyl ether. And so now we see that oxygen in the middle. One thing to notice here is that ethanol and ether are not flat. Oh, and I should say, actually, before we move on to this next point about their geometry, do note that the ether that's up here and ethanol, that previous molecule, are called isomers, ISOMERS. It's one of those vocabulary words you want to learn. And they have the same molecular formula, but they have different structures. So as I was saying, kind of this last point here is that you'll notice that this molecule isn't flat, and neither was ether. The electrons that make up these molecules, or these atoms, are all negatively charged, and so they try to get as far apart from each other as possible. Like charges repulse each other, opposites attract. So the electrons that are repulsing each other, they're getting as far apart from each other as possible. And so we can do from that some prediction about geometry of molecules. And so, if, for instance, here we have a water molecule, and the water molecule has these has an oxygen with two lone pairs, and then it also has two hydrogens down here. And so it has four different groups around the central atom, and so we call that electron geometry tetrahedral. The bond angle is 109 degrees, pardon me. So there's also another term that confuses students a lot called molecular geometry, and this is when we note that the lone pairs are pushing the atoms, the bonded atoms, down. And so if you kind of just don't look at the lone pairs and just look at the shape of the molecule or shape of the bonds to atoms, you can see that that's kind of a bent shape. And so this is called a bent molecule. If we look at ammonia, NH3, again, the electron geometry, there's four groups. To get four groups as far apart as possible, it's going to be tetrahedral. But this time there's one lone pair. It's pushing those groups down, and we call that trigonal pyramidal. CH4, on the other hand, there's no lone pairs. And when there are not any lone pairs, then the electron geometry and the molecular geometry are the same thing. One of the things that I would like you to memorize or to get in your head is the names of the different shapes. And so notice we just went through this top row here where in all of those cases, the ammonia and the water and the methane, they all had four electron groups. They all had an electron geometry that was tetrahedral. But the number of non-bonding groups or lone pairs were different, and so that led to different molecular geometries. A single molecule can have many different shapes, just like a bicycle has many different shapes in it. And so I think one of the problems that I have you do or ask you to do is to figure out the shapes at different atoms. And so here we have that carbon, and it has it has four things bonded to it, three hydrogens and a nitrogen, and so that would be tetrahedral. We have a carbon here, it's bonded to an oxygen, a carbon, and a nitrogen. So that's three groups, and according to our table, that's trigonal planar, and there's not any electron pairs to worry about, so it's just trigonal planar. Down here, it's actually not shown, but this nitrogen has to have a lone pair. And so it has a lone pair, and it has a carbon and another carbon, and so it's got those three electron domains. So again, it's trigonal planar, but it does have one lone pair, and so it would be considered bent.